Okay, let me welcome you to this second lecture of our class on reinforcement learning. Last time we talked a little bit about deterministic dynamic programming problems and their exact solution. And this lecture is going to be devoted to stochastic dynamic programming problems with both a finite horizon and also an infinite horizon. So we're going to do a little bit of review of the dynamic programming algorithm for deterministic problems, and also discuss methods of approximation in value space. Then we're going to go into the stochastic dynamic programming algorithm. We are going to apply to the exact solution of an important class of problems, linear quadratic problems involving a linear system and a quadratic cost function. This is an important special case, but also it's a very favorable case because it has an analytical solution, which is going to be also useful for us in constructing visualizations of various methods that we're going to be interested in. Then we will discuss approximation in value space for stochastic problems. And then another class of methods, approximation in policy space, which is receiving a lot of attention, but as far as this course is concerned, we're not going to spend too much time on it. We're going to briefly outline the ideas behind it in this lecture, and then near the end of the course, we're going to discuss methods for constructing such approximations. Then we're going to go to infinite horizon problems. We're going to overview their theory and their algorithms, and then discuss the application of the infinite horizon theory to linear quadratic problems in infinite horizon. Let's start with the finite horizon deterministic problems and a review. In the previous lecture, we defined this problem. It involves n stages, and the state of the system at stage k is denoted by xk. The control of the system is denoted by uk, chosen from some set that depends on xk. And at the typical stage, the state is xk. We apply control uk, and we move to state xk plus 1 according to this equation. And we also incur this cost, and we do this for n stages. The cost function is the sum of the costs over the n stages plus a terminal cost at the end involving the terminal state xn. Now, the control variables are uk, and there's a sequence of n of them, and we want to minimize the cost over this sequences of controls for a given initial state x0. So this is the expression corresponding, the expression for the cost corresponding to state x0 and the sequence of controls u0 to un minus 1. And the optimal cost function is obtained as the minimum over the controls of this expression, and it's a function of x0. We denote by j star. So this is the optimal cost function of the problem as a function of the initial state. And the dynamic programming algorithm for this problem involves a backwards computation to compute the optimal cost, jk star of xk, of the tail subproblems corresponding to the states xk. Okay, so how do we do this? We start with the final, the terminal subproblem, and this is the initial condition for the computation. And given jk plus 1 star, we compute jk star for xk by adding the cost of the kth stage, adding the optimal cost of the tail subproblem from the state where we land, and minimizing over all uk. This is dynamic programming algorithm. It goes backward from Jn star, computes Jn star minus 1, J star n minus 1, J star n minus 2, and so on. And at the last step, we obtain the optimal cost function of the problem, which is J0 star of x0. Now, this computation is quite substantial. It can be viewed as offline training. When we want to choose controls online, we go forward. And the way we do this is at the initial state, we do this minimization and obtain U0 star, go forward one step, obtain X1 star, and continue this way to obtain all the controls in sequence from U0 star to UN minus 1 star. This is what you would apply online to compute the optimal control sequence after you have computed all the J stars. Now, the dynamic programming algorithm can also be written in an alternative and equivalent way by using Q factors. The optimal Q factor corresponding to a pair of xk uk is defined by this expression. In other words, it is the cost of the stage corresponding to xk and uk plus the optimal cost to go from the next stage where you land. It is, in fact, the expression that appears in the right-hand side of the dynamic programming algorithm. So this is the definition. And now the optimal cost function, Jk star, can be obtained from the optimal Q factors by this expression. This is just the dynamic programming algorithm, minimum of this expression to obtain Jk star of xk. So now we can write the dynamic programming algorithm in terms of Q factors by combining these two equations. This Q factor here is given by this, and it's given by, and we have to add this, which is the minimum over UK plus 1 of the Q factor at the next stage. So whereas dynamic programming algorithm operates on optimal cost functions, costs to go, this alternative algorithm operates in terms of Q factors. And there are reasons in reinforcement learning why we want to consider Q factors, and this will become apparent as we go along. However, this alternative dynamic programming algorithm can be viewed as another way to do approximations. And approximate forms of this type of algorithm and related algorithms form a class of reinforcement learning methods which are known as Q learning. We will revisit Q learning later. We're going to focus primarily on cost functions. Okay, so now approximation in value space is the principal methodology that we're going to consider in this course. It tries to alleviate the problem, the major problem of the dynamic programming algorithm, which is overwhelming computations, by replacing Jk star with an approximation J tilde k during online play. The main problem here is computing these Jk tildes, which can be very, very difficult. So suppose that we have some approximation, and we're going to discuss methods for obtaining such approximations. Then we can do online play and generate online suboptimal control sequences by going, start from the beginning, compute U0 tilde by minimizing this expression where J1 star has been replaced by J tilde 1. Go one step forward and then sequentially go forward to calculate the remaining controls in the sequence. So an evident question is, how do we compute these J tildes? And this is one of the principal issues in RL. It's going to be occupying us for most of our course. There are many different ways to do it. And let me just summarize the principal categories. One possibility is to use offline problem approximation. Suppose we have the original problem and a simpler version of that, and we solve it exactly by dynamic programming. Then we can use the optimal cost function of that simpler problem as our J tilde for this approximation in value space algorithm. So that's one possibility. Another possibility is to do online approximate optimization, whereby it's solve online a shorter horizon problem by multi-step look-ahead minimization and a simple terminal cost function. In other words, our problem, our original problem, may have a long horizon. In this type of method, we consider a version of the problem over a shorter horizon, and then perhaps use some for multiple steps, perhaps, and also use a terminal cost function approximation at the end. And this is the principal type of method that's used in MPC, model predictive control. Here's another possibility: obtain these J tildes by training. Approximate them parametrically. Introduce a parametric class of functions which involve a parameter R, which is tunable, and then tune R by training using data and perhaps a neural network or some other approximation architecture. So this has to be done offline, of course, and basically we use neural network ideas to calculate from data this J tilde. It's a challenging type of methodology, but it's one of the principal ones within the landscape of reinforcement learning. Okay, the fourth type of algorithm, an example of how we compute J tilde, is by doing rollout with a heuristic, and we will explain this in the next few slides. In rollout, we calculate J tilde by using a heuristic from the next stage. In particular, we generate a single system trajectory, one state at a time, and at the typical state, upon reaching this state xk, we consider all possible controls, we compute the corresponding next states, and from each one of these next states, we run the heuristic, some heuristic algorithm, which is unspecified at the moment. It generates a trajectory all the way to the end, and also a cost. Now, the cost of the heuristic is denoted by xh of xk plus 1, xk plus 1. And for each one of these controls, we calculate this expression, and then we choose the control that minimizes this expression. So it is approximation in value space, with hk plus 1 taking the role of J tilde k plus 1. However, this heuristic is applied online through some kind of simulator or some kind of analytical calculation. And this is done for all possible values of the control. So from xk, we generate the next state after choosing q tilde k, and we repeat. And one by one, we get to the end of the computation. This is the rollout algorithm for finite state deterministic problems with one-step look ahead. There are multi-step look ahead versions also. So now let's give an example of this algorithm. And incidentally, your first homework is a more difficult version of this example. It involves the traveling salesman problem that I considered in the previous lecture and gave a problem formulation and an exact solution. Okay, what is the problem? We have a number of cities, 4 in this case, which I denote by A, B, C, and D. And we want to start at some city and go to and visit all the other cities once and only once. And there is a travel cost in going from one city to the next. given by this matrix here. So to go from city A, from A to B, it takes 5, it costs you 5, to C it costs you 1, to D it costs you 20, and so on. This table here, this matrix, gives you all the intercity travel costs. And we want to find the sequence of 4 cities with no repetition that starts at A and goes and returns to A. To formulate this problem, we did this last time. We have to introduce states, and the states are partial tours. So the initial state is city A. Partial tours of length 2 starting with A are AB, obtained by visiting state city B from A, AC, and AD. And then at this stage here, we add one more city that we have not visited before, and then one more city at this stage, and then we have to return to city A. Now, the travel costs are the black numbers that I have put in along those branches. Okay, you can check. A to B is 5, A to D is 20, and so on. And the dynamic programming algorithm, we did this last time, starts from the terminal state and goes back one step and gives you this red numbers here, and then goes back one step, gives you this red numbers here also, 20 plus 1, 1 plus 3, which is 4, and so on. Now, in this last two stages, there is no choice to be made. At this stage, we have a choice between 2 different cities to go, and the dynamic programming algorithm compares this branch and takes the minimum after adding the corresponding travel costs. So, so if you take this branch, is 21 plus 1 equals 22. Take this branch, is 4 plus 4, which is 8. That's where this 8 came from, is the optimal cost to go from this city. And so on, we do this from all cities, and we reach the initial state, and we compare 5 plus 8, which is 13, 1 plus 27, which is 28, and 20 plus 25, which is 45. 13 is the smallest, and this is the optimal first choice, go from A to B. And then we do the same thing, online play going forward, and we construct the optimal sequence, the optimal solution, which is go to B, and then to D, and then to C, and then back to A. So this is the optimal solution. Now, we want to apply rollout. Remember, in the rollout, at every state that we land, we consider all possible choices and then run this heuristic. And we're going to choose for this example a common heuristic, which is called the nearest neighbor heuristic. Basically, it goes from a given partial tour, from the end city of the partial tour, to the nearest neighbor that's eligible to be included in the next tour. So, for example, at this partial tour here, we consider the 2 possibilities, and we go to take the possibility of the smallest cost, like this one. So this is some kind of a greedy heuristic, and let's see how it works, starting from the initial state. So here we look at all neighbors, and the nearest neighbor is C, which has a 1. Here we look at the 2 neighbors. The nearest neighbor is 3, is D, which costs you 3. And then there's no choice at this partial tour. We have to choose B, and then we have to choose B. So this is the trajectory generated by the nearest neighbor heuristic, which in the parlance of rollout, we call the base heuristic. And now we are going to discuss how the rollout algorithm will work. Are there any questions so far? Is this figure understood? Okay. So remember, rollout goes forward, starting from the initial state. It considers all possible choices, and it runs the base heuristic from each one. So it goes over here, runs the nearest neighbor heuristic, which is 1. We go here, and here. Okay. So this gives me 5 plus 1 plus 1 plus 20. So that's 27. Okay. So that's what this blue number here is, 27. Then we consider the other option, which is to go to CDC. Then we run the base heuristic from there. It's this one. And it gives you a cost of 1 plus 3 plus 4 plus 20, which is 28. And then I consider the third option, go to CDB, and we run the nearest neighbor heuristic. Takes me here, here, here. So this gives me like 63. So the best possibility is this 27, and the rollout algorithm is going to move to this partial tool. It's going to choose B. And then it's going to, again, run the rollout routine. Consider all possible options, this one and this one, and run the base heuristic from there. Now, okay, the base heuristic, there's only one choice. We can see it here. And if we compare the numbers, 1 plus 1 plus 20 is 22, 4 plus 3 plus 1 is 8. This one wins. So after moving here, we change course. Instead of going here, we'll go here. And then there is no choice after that. So the rollout algorithm is going to generate this red sequence, which incidentally is optimal in this particular case. So that's how the algorithm works. And notice that there's something about it that's interesting and generalized. We started from an initial trajectory, an initial solution generated by the base heuristic. Then the rollout algorithm generated another trajectory, this T1 trajectory, which has smaller costs. From 28, we went to 27. Then it changed course again and followed this branch here, which has a total cost of 1 plus 3 plus 4 plus 5, which is 13. So the rollout algorithm has a cost improvement property. It looks forward all the way to the end, not like the nearest neighbor heuristic, which is greedy and looks only one step ahead. It looks all the way to the end and generates trajectories that are improving at every step, improving or of equal cost. You started with this trajectory, generated this trajectory, and then generated this trajectory. That's the important property of rollout on which we are going to expand quite a bit as we go along. It provides you with cost improvement, a better solution than the one provided than its base heuristic. And this is an example, and we have seen an example of that. Are there any questions about the rollout algorithm for this example?
Professor?
Yes?
Does rollout guarantee an optimal solution, or does it only improve the base heuristics?
In this example, it improves the previous solution, not just the base heuristic. We start from the base heuristic, get a better trajectory, and then a better trajectory after that, and so on. So from 28, we went to 27 to 13. Of course, I should tell you that some conditions are required for this. Generally, it is true when the base heuristic is greedy, okay, of the greedy type. However, we're going to be more precise as we go along, probably 3 lectures from now.
Professor, I have a question from a student in the room. One second.
Okay.
Hello, Professor.
Yes.
This is Abhishek. I have a question like, say, the travel cost from city D to city A is taken as 20. So if we take that cost as 21, then we might not get the optimal solution with rollout. Like we will then get the solution from city A to city AC, then that path will be followed. Maybe like rollout will give improvement from the best heuristic, but it's how good it is from the optimal, like is there any guarantees for rollout, or like what conditions should be followed so that we get good
You're right.
results?
The rollout algorithm is not guaranteed to give you the optimal solution. So not suboptimal solution, which is obtained much cheaper. That's the philosophy behind it. How well does it work? Well, it's difficult to quantify the cost improvement. However, one can get insight about how this cost improvement comes about. And this is through the mechanism of Newton's method. We're going to discuss this in the next time. You can view rollout as a one-step of policy iteration, the method of policy iteration, and also as a one-step of Newton's method, starting from the cost function of the base heuristic. So the Newton step will give you an improvement, and also if you're sufficiently close to the optimal, it will guarantee you a very substantial improvement. And we're going to see this in various examples. However, it's very difficult through analysis to quantify just how much improvement we're going to get. But we're going to be getting a lot, depending on whether we are within the sweet spot of Newton's method. That's basically the idea.
Thank you.
Okay. Any other questions? Okay, so now we're going to go into stochastic dynamic programming, and we're going to go from exact to approximate and so on. So in stochastic problems, when you transition from a state to the next state, the transition involves some randomness. If you choose, even if you, after you choose the control, there is no guarantee that you're going to land at any particular state. There is a probability distribution over the next states, which is determined by a random parameter, which we generically call disturbance, this WK. It has a known probability distribution, and it could take the character of any of a number of things, depending on the application. It could be physical noise. It could be market uncertainties in a financial type of problem. It could be demand for inventory, which is uncertain in a supply chain type of problem. It could be unpredictable malfunctions, like in a machine shop, some machines may break down, or some robots may break down. There is these disturbances, which make the problem more complicated. The random cost affects the system equation. The random variable, WK, affects the system equation, and also it affects the cost of the transition, which now takes this form here. Now, for a given sequence of controls, we're going to get a total cost that's given by this expression, like before. However, this cost is random. It is random because it involves the random variables WK. So to obtain a number, we're going to take the expected value of that, and we're going to call this the cost of a sequence U0 up to UN minus 1. However, here, we will not optimize over sequences of controls. Instead, we're going to optimize over feedback policies or closed loop control laws. Part of the definition of this problem is that when we land at a state xk, we get to observe it perfectly. That's the meaning of perfect state observation. When making the kth decision, we know the current state. So we can use that, and we can adapt our decision based on what state we observe that we're in. In this way, we don't have to stick with a decision that we choose. If we choose a sequence of controls at the initial state, we are not bound to that, but rather we are free to observe the current state and choose appropriately our decision. So the object of minimization is something more complicated now. It's a sequence of functions, not a sequence of controls. Each one of these functions, mu k, let's say, maps the current state xk into a control to apply at xk. It can be viewed as a lookup table, a table that tells you if you land at xk, you are going to apply uk. Another table for stage k plus 1. If you land at xk plus 1, you are going to use mu k plus 1 of xk plus 1. There are these n tables that characterize this feedback policy for closed loop control. We're going to be calling it policy. So here's an important point. Using feedback, choosing controls with knowledge of the state is beneficial in view of the stochastic nature of the problem. We overcome the uncertainty by choosing controls while incorporating our knowledge, our state of knowledge. We know that the states that we generate, we adapt our controls appropriately. And we optimize over all the possibilities. So now let's define the cost function. Given an initial state and given a policy pi, the cost of that policy is given by this expression. We plug the mu's of the policy inside the cost, and we get a random number, a random cost. Random because there's WK here. We take the expected value of that, the weighted sum of all these costs weighted by the corresponding probabilities of the W, and that gives us a number, not a random variable, a number that depends on the initial state and on the policy. Now we minimize overall policies, and that defines the optimal cost as a function of the initial state. And an optimal policy is one that attains this optimal cost, and we're going to see that the dynamic programming algorithm will give you a policy that's optimal for all initial states. So let's get into the stochastic dynamic programming algorithm. Similar to the deterministic case, it produces the optimal cost of the tail subproblems that start at the different states. And we use the same notation for this. The way you derive the algorithm is by some kind of a principle of optimality type of argument. Not quite the same, but it's inspired. The mathematical argument is inspired by the principle of optimality, and it's given in your notes. We're not going to go through the mathematical argument here, but the algorithm itself is very intuitive. It starts with the terminal tail subproblem and then goes backward. And it uses the same type of calculation as the deterministic case, involving the cost of the current stage plus the optimal cost to go from the next stage where we land. However, this expression here is random, so we take the expected value over WK and get a number for every U, for a fixed X, and for every U, we obtain a number, which is also the Q factor, okay? What we call the Q factor. We minimize overall U, and that gives us the optimal cost of the tail subproblem of stage K. So it's the same kind of algorithm as before, but it involves this W's and this expectation. And the optimal cost is obtained at the last step. The last function obtained, J0 star, is the optimal cost function. Moreover, from this algorithm, we can obtain also the optimal policy. And the optimal policy component mu k star can be constructed simultaneously with jk star with this calculation and consists of the minimizing uk star here. So we do this minimization for every xk. We obtain optimal controls to apply at each state, and we put them together into a policy component, uk star. Is this table of controls to apply at the different states. So the dynamic programming algorithm will give us both the optimal cost and the optimal policy. However, there's another way to obtain the optimal policy or to implement the optimal policy that does not require storage of these uk stars. Suppose that we have computed all the j stars, and now we want to implement online the optimal policy. We sequentially go forward. For every stage, we observe the current state and we apply the minimizing control. Remember, we have these j stars we assume here, and given the state xk, we minimize overall u, obtain the control uk star to apply, observe the next state xk plus 1, do this calculation again, and go forward. So these two methods are equivalent. This one requires a priori storage of the optimal policy. This generates it online, assuming that we know the j stars. But the fly in the ointment here is that there's a lot of computation still. We need to know the j stars. Even if we know the j stars, there's an issue with computing this expected value. Depending on the problem, this computation of the expected value can be quite time consuming. And remember, it has to be done for every u. And then we have to also minimize overall u, which is also involves some computation. So all in all, this algorithm is very, very time consuming for any kind of challenging problem. However, there are some nice problems for which this algorithm works nicely analytically. It can be used for analytical solution of the problem. And this is the favorable case of linear quadratic problems. It's very important in control theory, and it's going to be very useful for us, both in terms of its applications and also in terms of the visualizations that it can provide. Okay. We're going to consider problems involving a linear system and a quadratic cost function. And for simplicity here, we're going to focus on one-dimensional problems, where the state is just a scalar, okay? xk plus 1 is generated linearly from the preceding state, the control that you apply, and also there's an additive disturbance, random disturbance to be added. And A and B are given scalars. So this is the system equation. And the cost at stage k is this expression here. It's a quadratic in the state, quadratic in the control, and Q and R are given scalars which are positive. And there's also a quadratic terminal cost. So that's the system equation. That's the cost function. And what's the dynamic programming algorithm? Well, it's the algorithm I gave in the previous slide. It starts with the terminal cost and generates jk star as a function of xk by using this computation. Current stage cost plus optimal cost to go from the next state, expected value of that over w, and minimization over u. So we have applied the dynamic programming algorithm to this linear quadratic problem. And the nice thing about it is that it can be carried out in closed form. It's a very easy computation, and it yields that the optimal cost to go is a quadratic function of xk. Kk is a scalar that we can compute with a simple algorithm. And the constant here is something that does not play a role, because if you add it here, constant doesn't matter. So effectively, the optimal cost to go is quadratic. And because this minimization here involves a quadratic, it gives you a linear function of the state as your control. We're going to show also that the optimal policy is equal to a linear coefficient LK multiplying the current state. And this LK can also be computed by an easy algorithm simultaneously with KK. So this is the nice analytical solution of the linear quadratic problem for the one-dimensional case. There's another interesting fact about this problem. The optimal policy does not depend on W. Okay? It does not depend on the distribution of W. It does not depend on its variance, on its higher moments, whatever, as long as it has zero mean. I forgot to mention here that we assume that WK has zero mean. Okay, if it has a non-zero mean, then a similar kind of calculation applies. And what is true is that the optimal policy does not depend on the distribution of W, just on its mean, which is zero in this particular case. And this is known as the certainty equivalence property of linear quadratic problems. It says that you can pretend that WK is not stochastic, but rather is deterministic and fixed at its mean, and you are going to obtain the same optimal policy. So you can treat the problem as if it were deterministic. Now, for other problems, this is not true. On the other hand, it is a common approximation idea to use in reinforcement learning. Simplify the problem by fixing uncertain quantities which give us trouble by fixing them at their expected values or some other typical values. Okay, so I'm going to go in the next slide and give you an outline of the derivation of these results. However, I want to note here that all of these results generalize to multidimensional linear quadratic problems, where xk is an n-dimensional vector, uk is an m-dimensional vector. The scalars a, b, q, and r are then replaced by matrices. Okay, and the same type of calculation goes through, except that we need to use linear algebra to do the derivation. In this lecture, I'm going to be focusing on the I'm going to be focusing on the one-dimensional problem, and I'm going to give you the derivation in the next slide. Okay, before I go into this long calculation, are there any questions? The calculation seems a little bit overwhelming, but it's a standard calculation and it's also an easy calculation to understand. It does not use long formulas, but not difficult mathematics. Okay, so what we want to do is execute the dynamic programming algorithm and verify that we obtain the formulas for the optimal cost function and the optimal policy that I gave in the previous slide. So how do we go about it? We start with this terminal condition, the terminal cost, and write the dynamic programming expression, minimize over u, the first stage, the current stage cost plus the cost to go, as given by this quadratic expression. So we substitute this expression here. We write this as so, and then we have this quadratic expression, and we expand it, okay? using the quadratic formulas. So it's the square of this here, then the square of Wn minus 1, expected value of that, but this is just the variance of Wn minus 1, because remember, Wn minus 1 is assumed to be zero mean. And there's also a cross product term involving this and that and its expected value. And now this is zero because the expected value of Wn minus 1 is assumed to be zero. If it were not zero, we have to modify this calculation. So collecting terms and taking this thing here out of the minimization does not depend on you. Taking this thing out of the minimization because it doesn't depend on you. The terms that depend on you are what you see here, and we have to do this minimization. Now notice that this is a quadratic minimization over u, and it can be done easily. How to do this? We minimize by setting to 0 the derivative of this expression with respect to u. Now the derivative is equal to this, so we solve for u now, and we obtain a linear function of xn minus 1, this linear function, where Ln minus 1, the linear coefficient, is given by this expression here. Very easy to see this calculation. So now we have the minimizing control, and we can substitute in here the minimizing control. In here, for example, and then obtain, after some calculation, obtain Jn minus 1 star of xn minus 1 as a quadratic plus a constant term. Okay, the constant comes from here. The quadratic is obtained because u is a linear function of x. So this is a quadratic function of x. And we add a quadratic function, we obtain a quadratic function that has this particular form. Kn minus 1 is given by this expression here, involving a, b, r, and q. So we are done with the first step of dynamic programming, and lo and behold, we have obtained a nice form of optimal cost to go. It is quadratic, like this one is, so we can repeat this calculation using this instead of that, and going backwards, we obtain the final result. I'm not going to go into the details. It's evident from this calculation that it can be repeated all the way going backwards. It has the form, okay, the sequence of k's, k of k, capital K of k, is given by this expression here, from k plus 1, starting with kn equals k, I'm sorry. From k plus 1, we obtain k. So this recursion goes backwards, and simultaneously we can compute the linear cost coefficients of the controller, which is given by this formula. Okay, sort of a generalization of this formula, k plus 1 replacing q. So that's the complete solution of the linear quadratic problem, assuming zero mean disturbances. And it is a very easy calculation to do. Essentially, the result is obtained in closed form. Are there any questions about this slide? Okay, we're not going to be doing calculations like that. I wanted to give you this one because it's important, and also what we're going to be using in the future is the fact that this is the form of the generic form of the optimal solution. And there's also a version of this for infinite horizon problems that we're going to come to in a few slides. So let's make some comments about linear quadratic problems in general. The first one relates to certainty equivalence. the solution does not depend on the distribution of WK, only on the mean of WK, which is 0 in the previous calculation. And this, the effect of this is that the stochastic problem can be replaced by a deterministic problem, an idea that's going to be used that's going to be useful in more general problems in the reinforcement learning context. As I mentioned earlier, it's generalized to multidimensional problems, non-zero mean disturbances, and so on. It's generalized to an infinite horizon. We're going to discuss this essentially by taking the limit in the solution of the finite horizon problem as n goes to infinity. Now, here's a major generalization. So far, we have assumed in our stochastic dynamic programming context that the state is observed exactly, perfectly. However, there are important classes of problems that involve imperfect state observation, partial state observation. Effectively, instead of observing the exact value of a state, we obtain some measurements, which are linear in the context of the linear quadratic problem. And the optimal policy involves, again, can be obtained analytically, and it involves an extended form of certainty equivalence, where, again, the optimal control to apply is a linear coefficient, the same linear coefficient as for the deterministic problem, times the expected value of the state given the measurement. When we observe the state exactly, this is equal to xk. Now, in this context of partial state observation, we don't observe the state, but we can compute the expected value of the state given the measurements through some kind of an estimation procedure. Kalman filters are used in this context. We're not going to discuss them, but it's one well-known estimator to calculate this expected value here. Again, this is an idea that is used in the way of approximation in more general context to replace unknown or imperfectly observed states with their expected values provided by an estimator. So linear systems and quadratic costs are a starting point for other lines of investigation approximations. This is a very, very useful line of, very useful approach in designing controllers. One class of problems where linear quadratic formulations play an important role is model predictive control. Most of the applications of model predictive control involve a linear system at quadratic cost, but also additional constraints. In our formulation of the linear quadratic problem, it is important that there are no constraints on the control and no constraints on the state. In many realistic control problems, there are state constraints, like the car should stay within the road, or the velocity cannot exceed a certain bound, because otherwise the car is going to go off the road on a turn. Then other constraints are that there may be obstacles that the car has to be able to navigate through. So all of this imposes state constraints and control constraints, which are part and parcel of many of the model predictive control problems, and require an extension of the linear quadratic formulation, which is quite substantial, but still linear quadratic formulations and results play a role. So similar with state constraints are control constraints, again in model predictive control. Also, problems of adaptive control, where the system involves unknown or changing parameters. This happens, for example, in self-driving cars, robots. The environment changes, the system parameters change, and certainty equivalence ideas from the linear quadratic problem apply here in adaptive control, and we're going to discuss those probably in the next lecture. So this is an example of an exact solution of a stochastic dynamic programming problem. And let me say that there are very, very few of those that you can solve exactly. Usually the solution is through computation, and the computation can be overwhelming because of the computation requirements of the algorithm and programming algorithm. So this leads us to the idea of approximation in value space and the reinforcement learning method. Are there any questions from the linear quadratic problem? Okay. This is a busy figure, but an important one. It outlines the approximation in value space framework, where we replace the J stars with J tildes, okay? And when we land at a particular state, we do this minimization online, and we go forward to the next state. So this minimization is like the dynamic programming formula, except that J tilde is used in place of J star. And there are three approximations here. And they are more or less independent. They can be designed independently of one another. One is the cost to go approximation, finding J tildes, okay? Another one is this minimization here, which can be very difficult. Simplifying the minimization is an important idea in reinforcement learning and approximation in value space. The third approximation comes from this expected value, which again can be quite hard to compute. Even though it involves only one stage, and one random variable here, this expected value computation has to be done for all controls. So it can be a difficult computation, and we're going to see ways of approximating this expected value. So the three approximations, and each one has to be done can be done in a variety of ways, and the choices can be combined in a scheme, in an approximation value space scheme. And there are some variants of this structure here. One is to use multi-step look ahead instead of one-step look ahead. Here we look ahead only one step and then take the cost function approximation. In multi-step look ahead, we look forward multiple steps and then take the cost function approximation. Another possibility to simplify the minimization is when you have multi-agent problems involving multiple components, and then there are ways to simplify the minimization, which can be very useful and save a lot of computation time. We're going to look at multi-agent problems in the next lecture, but now I want to give you a figure for summarizing multi-step look ahead. So in multi-step look ahead, we look, instead of one step and then the cost function approximation, we look at L steps, minimization, and a terminal cost function approximation. And we minimize over the U of the current stage plus the policies that we're going to follow for the other L-1 stage. So what this is a dynamic programming computation involving L steps rather than N steps. And again, we have the three approximations: minimization, expected value, cost approximation, cost function approximation. And after we do this minimization at the current state, we use UK and throw away all the mu's that are found. So this is multi-step look ahead, and it tends to perform better than one-step look ahead. However, it requires also a lot more computation per stage. So there's a trade-off involving performance and computational overhead. And this trade-off is something that we're going to be discussing in our future lectures. And we're going to quantify what is involved in this type of trade-off. Okay, so here's a complementary figure. How do we construct approximations of different types? There are many different ways to construct cost-to-go approximation. We mentioned one of them, certainty equivalence. Pretend that the problem is deterministic by fixing the random variables, the random disturbances at some typical values, and then solve it in one way or another. Certainly, there's a big simplification. Another possibility is problem approximation. Replace J star by the optimal cost of a simpler problem and use this as J tilde. Rollout is one possibility, an extension of the deterministic rollout that I gave in the previous in deterministic problems. Model predictive control can also be fruitfully viewed in the context of rollout. Then another major class of approximations is through neural networks and approximation architecture. We find a J tilde by training with data and training a neural network in ways that we're going to discuss in future lectures. So that's one major possibility. Another possibility also is aggregation, where we consider a smaller problem where groups of states are aggregated in single states, and this aggregated problem can be solved more easily than the original. It has a connection also with problem approximation. So all of this is a very, very big chunk of reinforcement learning theory. And we can't cover everything, but we're going to nibble around various possibilities. Okay, how do we approximate this minimization? Well, the minimization here could be potentially be over a very large number of controls or an infinite number of controls. So how do we make this feasible? How do we make this tractable? Well, if we have a continuous control space, then one possibility is to discretize it, and that will simplify this minimization. Another possibility is selective minimization, whereby we have a large control set, but we select out a subset of promising controls. By means of some heuristic, we reduce the control constraint set to something that's smaller, and that will proportionally decrease the amount of computation needed here. We're going to discuss possibilities along this line as we go forward. How do we simplify the expected value calculation? Well, one possibility is, instead of full-blown Monte Carlo simulation, in situations where we cannot do this calculation analytically, have to use simulation. Instead of doing full-blown Monte Carlo simulation, we can do selective simulation, whereby we simulate more accurately controls that are more promising than controls that are sort of don't seem very good on the base of preliminary calculation. And this is the idea involved in Monte Carlo tree search. Monte Carlo tree search is a method for doing adaptive simulation and reduce the calculations of this expected value. And it can be used both in the process of offline training as well as online play. And it's a very big part of the success of AlphaZero, by the way, because AlphaZero requires very deep calculations for which exhaustive simulation of all the possibilities is very hard. And this tends to reduce the amount of computational effort that goes into the simulation. And so this extra time can be used for other things. improving this approximation. So all of this is part of our future algorithmic possibilities that we're going to discuss. And by the way, there are corresponding possibilities for multi-step look ahead. I'm showing here only the first, only the one-step look ahead. Let me give you the general structure of rollout. This is a possibility for approximation of the terminal cost. Here we use a base policy, like in the deterministic version of rollout, and some terminal cost function approximation. At a given state, we consider all possible controls and also all possible states that you may end up with, which means that we have to consider all the possible W's as well. And from each one of those, we run the base policy for a number of steps, m steps, or all the way to the end of the horizon. But if we don't run to the end of the horizon, we use a terminal cost function approximation for the stages beyond truncation. And then we calculate the Q factors that correspond to each of these controls, and we choose the control that has minimal Q factor. Are there any questions on the general structure of approximation value space for stochastic problems?
I have one question from a student here.
Okay. What is the question? You said you had one question?
Yeah, Professor, could you go back to the last slide? So my question is the J tilde, is it a fixed number?
J tilde depends on the next state. Okay, it's a function, right?
Okay.
So it involves uncertainty. It involves also uncertainty. It's part of the expected value.
Okay, I see. My initial thought is because this is trained offline, so I suppose when we know the xk plus 1, it should be a fixed number.
The functional form of J tilde is fixed. Like it may be a quadratic function, or it may be the output function of a neural network. The functional form is known, but the argument xk plus 1 is not. So if this were represented by a neural network, you would have to feed into the neural network xk plus 1 before it will give you a number at the output.
Okay, thank you.
Okay. So let's talk a little bit about approximation in policy space, and then we'll take a break. Approximation in policy space is the major alternative to approximation in value space. The philosophy is different, very different than in approximation in value space. What we have here is a system that has a state that we observe, and we apply a certain control to it using some policy. And then we keep going forward. Now, calculating the optimal control is very, very difficult, but we can consider a parametric class, a restricted class of policy, such as those provided, for example, by a neural network or some other type of approximation architecture. And this is a parametric class involving some parameter. Once you fix this parameter, Rk, then this controller is determined. But how do you find Rk? Well, you do this by optimization over in the parameter space. And this minimization may involve training data, may involve some measure of performance. We'd like to find Rk that leads to low cost, okay? So it may be an optimization over Rk to reduce the cost of the problem, starting from some initial state or from a subset of initial state. So that's the usual structure of the controller, parametric family of some form, for our case, a parameter. And the methods used for optimization are garden variety of optimization methods, random search, gradient type of methods, policy gradient methods they're called. And also methods that are used in machine learning for classification, as we will discuss shortly. So there's a large variety of methods, and there's an important advantage to this methodology. Once I have computed the parameters, usually offline, then I have a fixed controller which can compute controls in response to given states very quickly, much faster. I don't have to do approximation in value space, minimization, expected values, and so on and so forth. This is a very costly computation. With approximation in policy space, this computation is very fast. A lot of the computation takes place offline to compute the parameters, but once these parameters have been computed, online controls are generated very quickly. There is also an important disadvantage. Once we compute a controller offline, we are locked to a particular system environment, to a particular model. If this model changes over time, if the parameters change over time, then we are locked into this controller. We can't adapt. Whereas in approximation in value space, we can do online replanning, which means that we do the look-ahead minimization based on the new model of the system, the new conditions within the environment. There is also another disadvantage to approximation in policy space, which will become apparent when we progress later. It does not involve a Newton step, and it loses the quality of approximations that approximation in value space provides. In other words, there are performance limits that you can obtain with this methodology, even if there is no need for online replanning. And this is due to the fact that there is the formalism of Newton's method does not apply to this methodology. Now, here's another important difference between approximation in value space and policy space. The approximation in value space is primarily an online play method. You compute offline this, but online you have to make this computation. Offline training is used optionally to construct cost function approximations here, or for the one-step and multi-step look ahead, or policies for this middle portion of rollout. On the other hand, approximation in policy space is primarily an offline training method, which may be used optionally to provide a policy for online rollout, this middle portion of the approximation in value space architecture. So we have made the point in the previous lecture that it is very useful to build online play on top of offline training. However, approximation in values in policy space does not allow that. It does not allow you to take advantage of online play on top of offline training. So approximation in policy space in alpha 0 would give you a mediocre player. Whereas if you take that mediocre player and harness it within this offline obtained approximations, then you obtain a much stronger chess player. Okay, it's also possible to combine approximation in value space with approximation in policy space. Remember, the approximate cost to go function is J tilde. The J tildes that define the one-step look-ahead policy, mu tilde K, or the multi-step look-ahead policy, lead to a computation that's quite substantial. How do we simplify this computation? Well, one possibility is to take this suboptimal policy and approximate it by approximation in policy space. And here how this is done. We'll use approximation in policy space to represent the policy obtained by one-step or multi-step look-ahead minimization. In particular, we have this J tildes. So we can do a lot of these minimizations offline to construct a training set involving sample pairs, plug in different XK values, obtain different UK values, and do this for a large number of states. Let's say 1 million states. We do this calculation, we obtain the corresponding 1 million controls, and we have constructed a training set involving 1 million samples. Now, once we have this input-output pairs, we can fit some kind of an approximation architecture, some kind of a neural network to this training set, often by using least squares. So in particular, we can introduce a parametric function of policies, which involve a parameter RK, which may come out from a neural network formulation or other formulation. And then we estimate the parameters by fitting the architecture to the training set that we have here. So look at this minimization. It involves the squared errors between what the samples are for given states and what the architecture gives you as a function of R. So this is a measure of fit of the architecture to this training set, and it involves a summation of all the errors over the training set. 1 million samples, this involves a summation of 1 million errors here, and we find the parameter that gives you the best fit in the sense of least squared error. Now, this is a type of methodology that's used very frequently in machine learning. People know how to do it. In particular, it's used in classification methods, where policies are identified with classifiers. We're going to discuss this later. But the point I want to make is that this type of representation of the one-step look-ahead policy in policy space involves algorithmic ideas that are very well known, very well practiced in the field of machine learning. So these are the two major approximations in reinforcement learning. Approximation in value space, on which we're going to focus, approximation in policy space that we're going to use, we're going to discuss much less, and mainly from now on only at the end, near the end of the course. And let's take a 15-minute break. And when we come back, you may think of your questions, and then we'll continue with infinite horizon problems. So we'll meet in 15 minutes exactly. So are there any questions about the first half of the lecture? We talked about deterministic and stochastic problems, the finite horizon, and outlined the methodology of approximation value space with a little discussion of approximation in policy space. And now we're going to go into infinite horizon problems and extend some of the ideas of approximation in value and policy, in value space. So infinite horizon problems are similar to finite horizon problems. They involve a random system, a random transition described by a system function and a random cost. Main difference is an infinite horizon. And there's also one more difference. The system equation and the cost does not depend on K. We're dealing with a stationary system. And a cost that is non-stationary, it involves alpha to the K. Alpha is some number that is between 0 and 1. It could be 1. If, however, it's less than 1, then it's called the discount factor, and the problem is called discounted. And the meaning of alpha less than 1 is that costs far into the future counts was less than cost in the near term. And the discount factor alpha enters into the cost function here and has an important mathematical effect. It keeps this expression bounded as n goes to infinity, particularly if g takes bounded values, because then this expression is it cannot blow up. It involves a summation or a geometric progression, and mathematically this is important because as we take the limit of the cost over an increasing horizon, we don't want this cost to blow up and be infinity. So the presence of a discount factor has the effect of making this cost tractable and mathematically correct. So for a given policy, which now involves an infinite number of functions, this is a random variable. Again, we take the expected value for a finite horizon, and then we let the horizon go to infinity, and this is what we call the infinite horizon cost of policy phi, corresponding to initial state x0. And the optimal cost function is obtained by minimizing overall policy. And discounted problems tend to keep this cost finite because of what I mentioned earlier. This becomes the sum of a geometric progression, involving a geometric progression. However, problems where alpha is equal to 1 are also interesting. But in order to keep this cost finite, they typically include a special termination state. So basically, these problems are finite horizon problems, except that the termination state and the termination time is random and it's not determined a priori. So the horizon itself is kind of random. And in these problems, the objective is to reach or approach t at a minimum expected cost. So for example, games involve a termination state where the game ends. And other problems involve states where once you reach, you stay there. For example, linear quadratic problems of the type that we have discussed involve state 0. At state 0, this is a termination state, and that tends to keep the cost finite, even when alpha is equal to 1. So this is the framework. The infinite horizon cost is the limit of finite horizon cost. And the theory of infinite horizon problems also revolves around the relation between the infinite horizon results and the finite horizon results. In particular, there are 3 theorems in infinite horizon problems that you aim to, that tend to hold for each type of problem. They certainly hold for the easy cases, which are discounted problems, the finite number of states, but they also hold in modified forms for other types of problems. And the 3 theorems are on this slide. The first theorem says that the k stages optimal cost obtained by finite horizon dynamic programming, as you increase the horizon to infinity, approaches the infinite horizon optimal cost. Mathematically, j stars of x is the limit of j k's of x, where j k's of x is the k stages optimal cost starting from x, which is generated by this recursion. The 0 stages optimal cost is 0, going to 1 stage, 2 stages, and so on. There's a sequence of costs involved here. And this is really the dynamic programming algorithm for finite horizon problems in disguise. And to see that, okay, how you derive this equation from finite horizon dynamic programming, let's call Vn minus kx the optimal cost to go, starting at x and going forward for k stages. Then, by the finite horizon dynamic programming is given by this expression. Cost with k stages to go is obtained from cost in with k minus 1 stages to go, plus the cost of stage n minus k. So this is exactly the finite horizon dynamic programming algorithm. And now, if you divide this expression by n minus k and define j k's of x to be that, then you obtain this formula here. So, this is the formula for generating this terminal, this k stages cost. It's really the dynamic programming algorithm in this guy. Now, this leads to an algorithm which we're going to discuss in the next slide. It's called value iteration. There's another important result here. It says that J star satisfies Bellman's equation, which is this equation here. There's one equation like that for every x. And to get a sense of why this should be true, look at this formula here. Take the limit as k goes to infinity. You get j star over here, j star over here, and here's the Bellman equation. Now, the Bellman equation is very fundamental, and it is all of the analysis in infinite horizon dynamic programming revolves around it, and either its properties or how do you compute j star, or how you approximate it. Note that there is one equation for every x. So if there are a million states, there are a million equations here. If there's an infinite number of states, there's an infinite number of corresponding equations in Bellman equation. And the third result is that if you obtain a policy by minimization in this Bellman equation, in other words, if mu stars of x attain the minimum in the Bellman equation for every x, then the policy that you obtain in this way is optimal. This is an optimality condition. Notice that this is a special type of policy. It involves the same mu star at stage 0 as at stage 1 as at every stage. This kind of policy is called stationary. And it makes sense because at stage 0 and at stage 1, you're essentially faced with the same problem. You're looking forward for an infinite number of stages. So it would make sense that you would do the same things at the same state, whether you are at stage 0 or stage 0, stage 1, or stage k, any stage 100 or whatever. So these are the three analytical results associated with infinite horizon problems. And there are some other results, of course, sometimes special in particular types of problems and so on, but these are the major results. And there are also two major algorithms: value iteration and policy iteration. Value iteration is the formula, is given by the formula I gave in the previous slide, generating the k stage cost, except for one thing. J0 is not necessarily 0, but it can be arbitrary. And I put a question mark here because arbitrary requires some mathematical qualification. This is true for many problems, most problems, certainly for discounted problems, but not for all problems. So, but generally you expect this algorithm to be valid and to, in the limit, to generate the optimal cost function. The second major algorithm is policy iteration. Now, for years, this value iteration generates a sequence of value functions or cost functions. Policy iteration generates a sequence of policies, starting from some mu zero that's more or less arbitrary with some mathematical qualification here. So from mu zero, you get mu1, mu2, and so on, and the corresponding cost function. For a policy mu, we call J mu the cost of the policy rather than J pi, okay? Generates a sequence of stationary policies. Stationary policies are denoted by just the single common policy component, mu. So how does this policy iteration work? Well, the typical iteration starts with a policy mu and generates a new policy, mu tilde, with two steps. One is a policy evaluation step, which computes the cost function J mu of this policy. This is like a base policy. Now, the policy improvement step uses the J mu of the base policy to compute an improved policy, which we might use as a rollout policy, a mu tilde, using one step look ahead minimization. So policy evaluation of the current policy, policy improvement by this one step look ahead minimization, where J tilde basically is replaced by J mu, the cost of the base policy. So this is reminiscent of rollout, and indeed a single iteration of the policy iteration algorithm is the rollout algorithm for infinite horizon problems. Now, a question that arises here is, how do you calculate J mu? There are several possibilities for computing J mu. One is to solve the Bellman equation corresponding to mu. Okay, Bellman equation involves a minimization, but if we restrict attention to a single policy, we obtain this equation, which is Bellman equation restricted to the policy mu. How do you solve this equation? Well, you can use value iteration to solve it. It's an easier value iteration because it does not involve the minimization. Or you can use some other method. One thing that helps very much the policy evaluation is that this is a linear policy. Okay, what does that mean? It's linear in J mu. View J mu as a vector. Think of the case of a finite number of states, say n states. So J mu is an n-dimensional vector, one value for every state. Now, if you write this equation for that vector, it's a vector equation that is linear. And why is it linear? Because, okay, the J mu components are here, and we take the expected value of those with respect to W, and the expected value is a weighted sum, weighted with the corresponding probabilities of W. So expected value operation maintains the linearity of, is a linear operation. So this is a constant component. This is linear in J mu. So the right-hand side is linear in J mu. So we have a system of linear equations with an equal number of unknowns. For the case of n states, this is a system of n linear equations with n unknowns that you can solve with Gaussian elimination or any method that MATLAB gives you for solving linear equations. Of course, when the number of states is very large, this is a very large system of equations, which is why we may want to use approximation in value space or something similar, some kind of approximation method to solve this equation approximately. Another possibility for solving this equation is using special type of algorithms that are relying on simulation. For a given state, we can evaluate its expected value by Monte Carlo simulation. And then we can use an algorithm that solves solves the corresponding linear system. There are also special stochastic iterative algorithms for solving this equation. An important class of methods of this type is temporal difference method. And there's a famous method called TD lambda that belongs to those. We are not going to go very far along this route. We're going to discuss simpler and more understandable methods for policy evaluation as we consider approximate implementations of policy iteration. And we can consider exact versions of policy iteration and approximate versions. Okay, here's a schematic for an exact version of policy iteration. Remember that it generates a sequence of policies. Starting with a base policy, it produces a rollout policy. And then it replaces the base policy with a rollout policy and does this loop again and again and again. That's policy iteration. And the two steps that you have to do at each iteration is policy evaluation to obtain the cost of the base policy, the cost function of base policy, and policy improvement, which involves, okay, the Bellman equation minimization with J mu in place of J star, the formulas I gave in the previous slide. And a general property of policy iteration is that it's a sound algorithm in the sense that it gives in the limit an optimal policy. And I have a question mark here because there are some exceptions. There's quite a bit of mathematical analysis that goes along with this statement, but on the whole, and particularly for the type of problems that we're going to consider, policy iteration is a convergent algorithm in its exact form. Another important property is that policy iteration is much faster than value iteration. And this can be traced to the fact that it can be viewed as Newton's method for solving the Bellman equation, whereas value iteration is like a first order type of method and far more slow than policy iteration. On the other hand, policy iteration involves a lot more overhead in carrying out this computation. The third point I want to make is that policy iteration can be implemented approximately. There are many different implementations. And these approximate policy iteration methods are very central to reinforcement learning. I mentioned earlier that AlphaZero and TD Gammon use forms of approximate policy iteration. And this implementation can be done using a value network and also perhaps in some cases a policy network. You may recall that AlphaZero uses both a value network and a policy network. TD Gammon uses only a value network. And the schematic for this approximate policy iteration, it should be compared with the exact version. Again, you have a sequence of policies generated. Starting with a base policy, we generate a rollout policy. And then we use the rollout policy in place of the base policy, and we continue along this loop. And the policy evaluation is done approximately here using a value network. In other words, we obtain state cost pairs associated with the base policy, a training set associated with this base policy, and we fit some kind of an approximation architecture, like a neural network. This is one possibility. There are other possibilities also. In AlphaZero, this is what is done. Except that, okay, there are some variations, but that's the main idea. Now, once you have an approximate value function, an approximate evaluation of J mu, then you can perhaps do approximation in do a policy improvement, and then an approximation in policy space by using a neural a policy network. And however, you don't have to do that. You can go straight into policy improvement. So this box can be exact or it can be approximate. If it is approximate, it involves approximation in policy space and taking the corresponding one-step look ahead policy that's obtained by policy improvement, construct a training set, and then construct a policy network in the manner I gave towards the end of the first half of the lecture. All of this involves data, self-generated data, in other words, data from the system itself, simulation of the system itself. So sometimes this is called self-training or self-learning. And many different methods of this type, which we're going to discuss to some extent in this course. However, in this course, we're going to focus on just one loop of this approximate policy iteration, or policy iteration in general, and a single iteration of the first iteration of the policy iteration algorithm is the rollout algorithm. That's how rollout gets into the picture in the context of infinite horizon. It is a single iteration of the policy iteration method. Are there any questions here? Okay, so now let's talk about linear quadratic problems. Revisit the linear quadratic problem in an infinite horizon setting. Again, it admits an analytical solution. And as we will also see, it admits a visualization that's going to be particularly useful for us. So we have a linear system, and we're going to assume that's deterministic. The reason is that we don't want to involve any discount factor, and to keep the cost finite, over a infinite horizon, we need to drop the uncertainty, the WK. However, the results that we're going to obtain are relevant also, as we will see, to stochastic problems by means of the idea of certain equivalence. So this is the system. This is the quadratic cost. A, B, Q, and R are given. Bellman's equation is given by this expression. So if you can find a J that satisfies this equation, then it's likely the optimal cost function. So how do we solve this problem? Well, we may use the ideas of value iteration and take the limit of the n-step horizon results, which say that this sequence of generated k quadratic cost coefficients converge. To take the limit of that, they converge to some k star, and this LK converges to some L star. And this suggests that the optimal cost function over an infinite horizon is of this form. It is a quadratic involving a scalar k star to be determined, some positive scalar, but it's quadratic in x. And the optimal policy is linear of this form, where L star is again some scalar. And to verify that indeed this is true, and to characterize k star and L star, we plug in J star of this J of this form into the Bellman equation, and we see what are the solutions of Bellman's equation. The Bellman's equation takes this form here, and now the nice character of linear quadratic problems emerges in the sense that this minimization involves a quadratic in U. So this quadratic can be done in closed form. In fact, the same calculation I gave earlier for linear quadratic problems. And after you do all the calculations here, take the derivative of this, set it to 0, plug in, and so on and so forth, it gives you this minimization is equal to this expression here, a quadratic expression involving this scalar that depends on k, f of k, given by this formula. Now, if you go back to the calculations for finite horizon of linear quadratic problems, you will see this expression coming into the value, the dynamic programming algorithm. So this is an easy calculation, and I think it's in your notes. I'm pretty sure it's in your notes, and you can check it there. Now, moreover, when you do this minimization, the minimizing u turns out to be equal to this. Okay, so this is a quadratic in u, and when you take the derivative, it is linear in x, and after you solve, you obtain that the minimizing u is given by this expression. So this gives you k star as the solution of this Bellman equation, and mu star as being equal to this, which means that L star is equal to this linear coefficient here. So the upshot, here are the results. The Bellman equation is solved for J star equals K star x squared, with K star being the solution of this equation here. K equal to Fk. This equation is famous, has a name. It's called the Riccati equation, named after an Italian count from the 17th century who invented the Riccati differential equation, and this discrete version of this Riccati equation from differential equations. And it's a very famous equation in control theory. And it gives you, when solved, it gives you the coefficient of the optimal cost function, this K star. And the second result is that the optimal policy is linear of this form, with L star being what you see here. So this all comes by arguing in terms of the infinite horizon Bellman equation, and it tells you that what you have to do. You have to solve this Riccati equation, and after you solve it, you just plug in the result in here and get the optimal policy. So let's look at these issues. How do you solve the Riccati equation? Are there any questions here on the slide? Okay. For one-dimensional problems, we can solve the Riccati equation graphically. For multidimensional problems, we can solve the Riccati equation analytically, characterize it, and but the graphical solution is going to be particularly interesting to us. Derivations are more or less the same, but the one-dimensional result in its graphical representation is very insightful for our purposes. Remember the Riccati equation. It says that K must be equal to this expression here, right? So we plot this expression, this f of k, it's this red curve, and it is a function of k, right? It's a nonlinear function because it involves k in the denominator as well. It turns out that it is a concave function, okay? Goes like this, has a negative second derivative. Moreover, it approaches asymptotes, okay? On the horizontal, it approaches an asymptote when k goes to infinity, okay? You can calculate the asymptote from this expression. And when k, and also there's another asymptote, when the denominator here goes to 0, okay? When the denominator approaches 0, which happens for the value of k equal to minus r over b squared, then the graph of the right-hand side of the Riccati equation goes off to minus infinity. So this is the form, and this is generic. It crosses the vertical axis at this positive number here. So this is a realistic picture. Now, how do we solve graphically the Bellman equation? We have to make the graph of the right-hand side, which is the red curve, meet the graph of the left-hand side, which is this 45-degree line. So this is a solution of the Riccati equation. There's a positive solution right here. There's also a negative solution, but the negative solution is not of interest to us because we know that the cost function of the problem is a positive definite quadratic. So only the positive solution is relevant. So this is K star. We plot the graph of the right-hand side of the Riccati equation, intersect it with a 45-degree line, and we get the solution of the Riccati equation. Now, how does this relate to Bellman's equation? Well, you can view the Riccati equation as the restriction of Bellman's equation in the space of quadratic functions. The Bellman equation is defined over a very, very broad class of functions. Every function is potentially a solution. But if we focus attention on the quadratic functions, then we obtain the Riccati equation. So that's the connection. The Riccati equation is a restriction of Bellman's equation. It says the same things as Bellman equation, but only along a subspace of interest, which are the quadratic functions. Okay, are there any questions about this graph, which we're going to be using a lot in the next lecture? Okay, so now let's visualize value iteration in terms of this Riccati equation graph. Now, value iteration has this form: jk plus 1 equals to something that involves jk, okay? The Bellman equation involving minimization involving jk in place of j star. So it has this form here, where kk plus 1 is the cost coefficient of jk plus 1. Kk is the cost coefficient of jk. And now if you cancel on both sides x squared, you obtain value iteration as a Riccati equation operation. Start from some k0, obtain k1, k2, k3, and so on, each time using the Riccati function f. So in value iteration, we start from some k0, some quadratic, and perhaps k0 equals to 0, okay? Perhaps something else. And at the typical iteration, we are at kk, the typical iterate, and we want to find kk plus 1, the next iterate. How do we do this? We have the graph of this concave function, like this. We are at fk, at kk. We calculate f of kk, which is this point here, right? This is f of kk. And now we reflect this over the 45-degree line over here. And this is kk plus 1. Kk plus 1 is this level. This is the 45-degree line. So this is kk plus 1. Now we go up again. We calculate f of kk plus 1. And kk plus 2 is this, and so on. So value iteration is represented graphically by doing this staircase with this staircase construction. Starting here, we go here, then here, then here, then here, and so on. And we converge this way to k star. We can start also on the right-hand side. And then We go over here, go down, over here, and so on. Notice that if you start from above, the convergence tends to be a lot faster. But it converges from any starting point, even from negative values, actually. This third case construction converges to K star. So this figure immediately gives you visually the verification of the convergence of value iteration, and it gives you also an idea of how it works. It's a very insightful figure that we are going to use in the next slide to get further insight, and we're going to use we're going to use a similar figure for policy iteration and also for rollout and also for approximation in value space. All of these methods that I have been talking about in summary in a somewhat abstract way can visually be made very transparent using this type of graphs, which are very insightful and suggest also modifications and alternative methods. So all of this is going to be for the next lecture. Are there any questions about this figure? Okay, so what's in for the next lecture? We're going to start with linear quadratic functions, linear quadratic problems, and discuss visualizations, in particular, interpretations of the Newton step. In addition to, we're going to interpret policy iteration as also as Newton's method. In particular, approximation in value space will be viewed as a Newton step for solving the Riccati equation. Now here we make a connection between the exact theory of linear quadratic problems and reinforcement learning methods such as approximation in value space. We're going to view a rollout as a Newton step starting from the cost function of the base policy. And again, we're going to use the Riccati equation graphs to make this interpretation. And we're going to interpret policy iteration as a repeated rollout and therefore repeated Newton steps. So this is the initial part of the next lecture. And then we are going to take a broad swipe at various problem types that are common in reinforcement learning. The first question is, how do we formulate dynamic programming models for practical problems? Then we're going to discuss problems involving a terminal state, which we're going to call stochastic shortest path problems. These problems, when they are deterministic, they reduce the shortest path problems, but we're going to talk about stochastic versions of shortest path problems that involve a terminal state. Then we are going to talk about various reformulations involving correlations between random disturbances, delays in the system equation, forecast. How do we formulate a problem into a dynamic programming problem if the basic assumptions of dynamic programming are not satisfied? There are reformulations which also lead to the view that dynamic programming can be used to model everything. It's also a matter of reformulating the problem by using some form of state augmentation. In particular, problems involving imperfect state information. Remember, we made a distinction. We have talked so far about problems of perfect state information, but problems of imperfect state information, which are also called in the literature POM DP, are very useful in practice. We're going to be able to reformulate them into problems of perfect state information so that the dynamic programming ideas and the approximation in value space ideas that we have discussed in this lecture apply to them as well. Then we're going to talk about multi-agent problems and see how we can fruitfully model them as single agent with single agent type of dynamic programming. Finally, we're going to talk about adaptive control problems where the system is either unknown and we have to estimate its parameters, or the parameters are changing and we have to re-estimate them as they change. So we have a lot to cover next time. And please read your class notes. Your class notes have been updated from last week. They are now more polished, okay? We're going to be polishing the notes even further, and also chapter 2 and 3 of the notes are posted now. Please try to read the notes as carefully as you can, and also if you find any points where they are unclear or they have flaws or typos, you may bring them to my attention. But try to read as much as you can in preparation for the next lecture. And also, as I have sent out an announcement, your first homework is due in 1 week. Before the beginning of next Wednesday's lecture, your homework is due, and it's exercise 1.1 of the class notes, so the first chapter of the class notes. Last time, I also noted the rules that govern the homework. You're free to collaborate, you're free to look at the solutions. However, you have to write your own solutions, and you have to write your own code and submit it to us to check it that indeed, okay, you've done the work. Are there any questions on this lecture, on this, or about the next lecture?
One
Everything
question
clear?
from a student.
Yes,
1
please.
second.
Please, yes.
1 second.
Hi there. For the homework, it looks like A, B, and C, we got a little graph that talked about how the one-step rollout works out, and then we'd add two-step rollout. So is the homework implementing this in code and then implementing each one of the A, B, C, D problems in code and kind of analyzing it? Or is it drawing the graphs, or what kind of format are you looking at?
Okay, this problem actually can be solved by hand, okay? You don't need to write a code. It can be solved by hand. It requires a little patience, but it can be solved by hand. So we want to see your hand calculations.
That's a lot easier, thank you.
And then you can, you're free to do paper and pencil type of solution. So yeah, you can do that.
Sounds perfect, thanks.
Okay. Some of you are more comfortable with code, but there's something to be said about a paper and pencil solution, if it is possible, of course. This is an easy homework, okay? Subsequent homework, just to get sort of your feet wet. Subsequent homeworks are going to be a little bit more challenging, but not that much more challenging. And they're going to have the same format: some analysis, a given problem formulation, some analysis, and some computation. That's the general structure of the homework for this course. Any other questions? Okay, guys, I'll see you next week, but I'm also anxious to see you use the Slack forum that Jameson has implemented. I hope you'll take advantage of that. I hope that you'll be talking with each other. You have an opportunity now, since you are, a large number of you are in the same classroom, and so you can see faces. But you can also, I'll be pleased to see you interact through Slack, and I look forward to getting involved as well. So see you next Wednesday.